Hello and welcome to the lecture session. In this video, I am going to explain about the half-range Fourier series. So, half-range Fourier series is nothing but when f of x is defined in the interval 0 to pi or 0 to L, then we represent f of x as a sine or cosine series only. These series are said to be half-range series, and there are two types of series. One is half-range cosine series, another one is half-range sine series. If f of x is defined in the interval 0 to pi, then the half-range Fourier cosine series is given by f of x is a0 by 2 plus sigma an cos nx, where a0 is given by 2 by pi integral 0 to pi f of x into dx, and an is given by 2 by pi integral 0 to pi f of x cos nx dx for n is equals to 1 to infinity. If f of x is defined in the interval 0 to L, then the half-range Fourier cosine series is given by f of x is a0 by 2 plus sigma an cos n pi by L of x, and a0 is given by 2 by L 0 to L f of x dx, and an is given by 2 by L integral 0 to L f of x cos n pi by L of x dx, where n is 1 to infinity. Next, half-range sine series. If it is defined in the interval 0 to pi, then the half-range Fourier sine series is given by f of x is equal to sigma bn sin nx, and bn is given by 2 by pi integral 0 to pi f of x sin nx dx for n is equals to 1 to infinity. If f of x is defined in the interval 0 to L, then the half-range Fourier sine series is given by f of x is equal to summation bn sin n pi by L of x, and bn is given by 2 by L integral 0 to L f of x sin n pi by L x dx for n 1 to infinity. Let's see the problems now. Find half-range Fourier cosine series for f of x is equal to x minus 1 the whole square, where x is from 0 to 1. Consider the given function, that is f of x, in the interval 0 to 1. So when it is equated to the interval, we get L is equals to 1. And from the Fourier cosine series formula, so we have f of x is a0 by 2 plus sigma an cos n pi by L of x, which is equation number 1. So now let's determine the a0 value and an value. Okay, so a0 value is given by the formula 2 by L integral 0 to L f of x, where this f of x is given by x minus 1 the whole square, which can be expanded or it can be integrated as it is. So when we integrate this x minus 1 the whole square, we get x minus 1 the whole cube divided by 3. Okay, so when it is substituted as upper limit 1, that is 1 minus 1, it will be 0. So this part will be 0, and this is minus 1 power 3. So it's actually minus 1 cube is minus 1 again. Minus of minus 1 will be plus 1. Therefore, we are getting a0 is equals to 2 by 3. Now let's find out the value of an. So an is given by 2 by n integral 0 to L f of x into cos n pi by L dx, 2 by L integral 0 to 1 x minus 1 whole square into cos n pi by L of x into dx. That is 2 times of x minus 1 whole square into sin n pi x by n pi minus 2 times of x minus 1 into minus cos n pi x by n pi whole square minus 2 times of the derivative of x minus 1, that is the second time. This one, if you differentiate, it is 2 times of 1 minus 0 into integral of cos will be sin n pi x by n pi cube. Now anyway, this sine term will be 0 whether we substitute the upper limit or the lower limit. So we are getting only the middle term, that is cos term. Here we have minus and minus, it will become plus. So what we are getting is 2 times of x minus 1 into cos n pi x by n squared pi square. When we substitute upper limit 1, 1 minus 1 is 0. Therefore, the first term will be again 0. Then the second upper limit, lower limit, when we substitute cos n pi 0 or cos 0, which is 1. And here minus of minus will be plus. Therefore, the an value is 4 divided by n square pi square. So an is given by 4 divided by n squared pi square. Let us substitute in the f of x. So f of x is given by a naught by 2, that is 2 by 3 divided by 2 means 2 and 2 cancels, 1 by 3 plus sigma an value is replaced here, that is 4 divided by pi square n square into cos n pi by L of x. That is, on simplification we get 1 by 3 plus 4 by pi square sigma cos n pi x by n square, which is the required Fourier series expansion. Let's look into the next question. Expand f of x equals to e power minus x as a half-range Fourier sine series in the interval 0, 1. Consider the Fourier sine series in the interval 0 to 1, where f of x is given by bn sin n pi by L of x. Let us call this as equation number 1 and consider the given function in the interval so that we get the value of L as 1. So consider this bn. Bn is given by 2 by L integral 0 to L f of x into sin n pi by L of x dx. So 2 by L integral 0 to 1 e power minus x into sin n pi x dx. Which on integration, that is by using the formula that is as I told you already, e to the power ax into sin bx. The integral of this is given by e power ax divided by a squared plus b square into a sin bx minus b cos bx. This is the formula which we have applied here. You can refer here. E power minus x by 1 square plus n square pi square and minus 1 sin n pi x minus n pi cos n pi x. Now anyway, again the sine term will be 0. We get only the cos term. Cos n pi is minus 1 power n. Cos 0 is 1. Therefore, minus 1 by e into minus 1 power n plus 1. This is given by e minus of minus 1 power n by e. That is multiplied with 2n pi by 1 plus n squared pi square. This is the value of bn which we can substitute in f of x. So f of x is given by sigma 2n pi by 1 plus n squared pi square into e minus of minus 1 power n by e into sin n pi x. So e power minus x is given by 2 pi by e into sigma n of e minus of minus 1 power n by 1 square plus n squared pi square of sin n pi x, which is the required Fourier sine series. Thank you.